We are finally ready to prove the mean value theorem. And now that we know the proof of Rolle's theorem, the proof of the mean value theorem is not that hard. You will see. So here I have the two statements, the statement of the mean value theorem and the statement of Rolle's theorem. If you look at them, the first two hypotheses are exactly the same thing. We need the function f to be continuous on the closed interval ab and differentiable on the open interval ab. Now, the difference is that the mean value theorem tells me that if I know those two things, then I can find a point C between A and B such that f prime of C is equal to f of B minus f of A over B minus A. Whilst Rolle's theorem adds another hypothesis. It asks that if f of A is equal to f of B, then I can find a point C such that f prime of C is equal to 0. So if you take a look at that, if we add the condition f of A equals f of B to the mean value theorem, well, we will end up with f prime of C equals to 0. So that means that the mean value theorem implies Rolle's theorem. And in this video, we're going to prove that Rolle's theorem implies the mean value theorem. So these two theorems are equivalent. They are actually the same result, just looking a bit different. So let's try to get this proof going. The idea behind the mean value theorem is the following. Here, the conclusion of the mean value theorem tells me that I can have a point C for which the tangent line to the graph at point C f of C is parallel to the secant line going through the points A f A and B f of B. So what we're going to do is we're going to tilt our heads a bit, and now the picture just looks like that. So the only thing that we did is we rotated a bit our picture. We now made those pink lines horizontal, and well, that now tells us that in that new picture, after rotating, f of A is equal to f of B. And the tangent line now is horizontal, so f prime of C is actually 0. So what we need to do is we need to find a way of replicating the idea of take the picture, rotate it or tilt your head a bit, and use Rolle's theorem. So that is what the proof boils down to. So how can we do this? Well, here we have the white line. Here is the graph of my function f. This blue line is the secant line passing through the points A f A and B f B. And now we're going to define a new function that I'm going to call h of x that gives us the distance between my function f and that secant line passing through the points A f A, B f B. If you look at it, well, the distance between these two functions at A and B is 0. As you can see, they just get close to each other, then they separate, and they join back again. So now, what I need to know is, well, what are the values at point x? Well, f of x, we have it, is this height that I have here indicated. And then, what can I say about my line at x? What is the y corresponding to that x, my blue line? Well, this blue line is what? Well, it's a line that passes through the point A, F, A. And we can compute the slope of this line as well quite easily. The slope would be, well, f of b minus f of a over b minus a, for example. So if I use the point slope form for a line, then I can see that this height up to the blue line is given by f of a plus f of b minus f of a over b minus a times x minus a. So if I want to know what h of x is, this pink distance here, all I need to do is f of x minus this blue, the distance here written in like this dashed blue line, that height. So then h of x becomes just f of x minus f of a minus f of b minus f of a over b minus a times x minus a. And if you see, when x is equal to a, we have f of a minus f of a. They cancel each other. And then we have f of b minus f of a over minus a. And then, well, we have a minus a, that's 0. So the whole thing is going to be 0. And the same thing is going to happen when x is equal to b, because we're going to end up with f of b minus f of a minus f of b minus f of a. So it's 0. So now that we have this function h, we just need to see how we can apply Rolle's theorem to my function h. And then we will see that we can just gain very easily the result of the mean value theorem. So the hard thing in this proof is finding this function h, is how I can find a way to tilt my head algebraically to get a formula for my function so I can actually use Rolle's theorem. You see, h is continuous in the closed interval ab and differentiable in the open interval ab because I know that f is, and I also know that, well, my function g of x given by f of a plus f of b minus f of a over x minus a times x minus a is also differentiable in the open interval ab and continuous in the closed interval because this is just a linear polynomial, so it's differentiable everywhere. We already discussed that h of a is 0, we know that h of b is 0, so we satisfy all the conditions for Rolle's theorem. So we know that I can find a point c between a and b such that h prime of c is equal to 0. But now let's try to write what h prime of c is. Let's try to expand it out and we'll see what we get. Well, we have that 0 is equal to h prime of c, but h prime of c is, well, is f prime at c minus f of b minus f of a over b minus a. Oh, but now if we rearrange this equation, we end up with exactly what we wanted, that f prime of c is equal to f of b minus f of a over b minus a, which is exactly what we wanted to prove.